This is the fifth thermal physics lecture. In this lecture, we're going to be finishing off looking at ideal gases. We'll be considering adiabatic processes, and then we'll be going over a few definitions. Actually, we're going to look at textbook sections 19.9 and 19.2. We're also going to have a quick look at how combustion engines work. This is not accessible. So first of all, just a quick recap of the ideas from the last lecture. We saw that for a gas, dW was equal to minus PdV. This is the differential form of the work equation. We can integrate it and we see that work is negative the area under the curve on the PV graph. As a gas expands, the gas is doing the work, so the work is negative, the gas is losing that energy. When the gas contracts, we need to do work on it, and so a contraction has a positive work. We saw that heat added to a system to get from a state with VI, PI and TI, so those are the initial volume, pressure and temperature, to a state with final volume, pressure and temperature VF, PF and TF changes depending on the path we take. So there's not a fixed amount of heat involved in getting from one state to another. It depends on how we get between the states. We saw that there's molar specific heats for gases, and that molar specific heat is the energy that needs to be added to raise the temperature of 1 mole of gas 1 Kelvin. And these are given for constant volume and constant pressure processes. We also derived the expression that the molar specific heat at constant volume was equal to F over 2R, where F is the number of degrees of freedom, and the molar specific heat at constant pressure is related to the molar specific heat at constant volume through Cp minus Cv is equal to R. These formulas are given to you on the formula sheet. Okay, on to new material. Adiabatic processes. An adiabatic process is one in which no energy enters or leaves the system as heat. So Q is equal to 0. So in reality, the way that we can do this is we can have a really well insulated container so that heat cannot pass easily through the walls, such as a thermos. The other way to do it is to perform a process quickly. It takes time for heat to flow from a hot body to a cold body, so if we perform a process very quickly, there is no time for the heat to flow. So for adiabatic processes, by definition, Q is equal to 0, so our first law of thermodynamics tells us that the change in the internal energy is equal to the work done on the system. So this is just an interesting example to consider, adiabatic free expansion. Imagine that we could concentrate all the molecules inside a piston into the lower half of the piston. We'll put a very thin membrane between them, and then we very gently, without applying any force or doing any work, break that membrane. In this case, what is going to happen to the temperature? Well, it turns out that the temperature doesn't actually change. As we're not adding any heat and we're not doing any work, the change in the internal energy, there is no change in the internal energy, and so there can be no change in the temperature. In this case, as it is obeying the ideal gas law, the volume's changing, and so the pressure that the gas exerts on the walls is also changing. So let's have a look at engines, because these have slightly more interesting adiabatic expansion and compressions in them. So we're going to look at a gasoline or diesel engine. They work in a very similar way. It's just exactly when the fuel is injected that is a little bit different, and the fuel itself. So this engine has 4 strokes. Initially, we have the fuel, or in the case of diesel, just the air, injected into the chamber. This has a constant pressure because it's got the same pressure as just outside the valve. After that, so this is the intake stroke. After the intake stroke, in which the volume increases, the volumes then compress. The valves are closed so that the gas cannot escape. This happens very quickly, so this is actually an adiabatic compression. At this point in a diesel engine, the fuel is injected and it's at a very high temperature. In a gasoline engine, a spark is ignited, and this causes the pressure to increase very rapidly while the volume's held constant because the piston's in the same place. As soon as that's happened, the gas expands quickly. So again, this is an adiabatic process because it's so quick, and this is where we actually get the work done by the engine. So this is an expansion and it's adiabatic. At that point, the exhaust valves open, and so the pressure drops to the external pressure, and the cylinders then compressed again in order to get rid of all the excess gas inside the cylinder. The engine has 4 strokes to ensure that one of those pistons is always undergoing the expansion, i.e. one of them can always provide the work to keep the shaft turning. Okay, now we're going to derive the relationship between P and V for an adiabatic process. This is a long derivation and you do not need to reproduce it. You just need to see it so that you're not taking my word for this equation being true. You can see it's true for yourself. For an adiabatic process, the change in internal energy is just equal to the work done. So P delta V, P dV is the integral form of that. Now, this is a slightly tricky step in this. We've said previously that it doesn't matter what path we take to get from one isotherm to another, the change in internal energy is the same as the change in temperature is the same. So the change in internal energy, keeping the volume constant, is given by NCV delta T, and that is going to be the same as the change in adiabatic, as the change in energy for this adiabatic process. So we can write this differential form P dV is equal to NCV dt, just replacing the deltas with the d's as we're considering very small incremental changes. Now we have our ideal gas equation, PV is equal to nRT. For adiabatic processes, PV and T can all change. P and V are both dependent on T. So what we're going to do now is differentiate this equation with respect to temperature, capital T. To do that, we're going to need to apply the product rule to the term on the left-hand side. So we'll leave P constant and differentiate V, and then leave V constant and differentiate the P. When we differentiate the right-hand side with respect to T, we just get 1 because T dt is 1, so we end up with nR. Okay, so this is our derivative here. Now what we'll do is we'll just multiply all the sides by dt to simplify it a little bit. So we've got P dV plus V dP is equal to nR dt. Okay, now this is just what we had on the last slide. On the slide just before that, we showed that minus P dV was equal to NCV dt. This was the constant volume case, and this was the adiabatic case, but the change in internal energy was the same. So what we're going to do now is replace this dt with this dt. So dt is equal to minus P dV on NCV, and so we're just replacing that now. These n's will cancel out, and we have P dV plus V dP is equal to minus R CV P dV. Now what we want to do is we actually want to get rid of this R. So we showed last lecture that Cp minus Cv was equal to R. So we're going to replace the R and divide by PV. When we do that, we end up with dV on V plus dP on P is equal to minus Cp minus Cv on Cv dV on V. Now, last lecture we defined this thing called gamma. We said that Cp on Cv was equal to gamma. So what we'll do is we'll replace this Cp on Cv, that's minus Cp on Cv, so that's the minus gamma. And then Cv on Cv is just 1, and that's minus minus, so we've got a positive 1 there. Okay, So we've got dV on V plus dP on P is equal to 1 minus gamma dV on V. Let's put all the dV's together. This dV will cancel that dV, and we'll end up with dP on P is equal to minus gamma dV on V. Now we're just going to integrate everything. When we integrate 1 on x, we end up with log x. So if we end integrating, we get log P plus gamma log V, moving this over to this side, is equal to some constant. We need the constant as we've done indefinite integrals. Okay, now we're going to apply our log rules. We can write this expression here as log V to the power of gamma, and then log P plus log V to the power of gamma. Adding two logs, we can multiply the things within the logs. So we have log PV to the gamma is constant. Now we'll raise e to the power of this side and to the power of this side to get rid of our log. We have PV to the gamma is equal to some constant. This constant is a different constant to the constant here, but they're both constants. Okay, so the equation for the relationship between P and V in the adiabatic case is PV to the gamma is constant. Now remember, gamma is Cp on Cv. You're given that on the formula sheet. A question to practice using this equation is 1131 set 4, question 9. It's a very hard question. And now it's left as an exercise for you to show that Tv to the gamma minus 1 is constant. The easiest way to do this is just to use the ideal gas law to replace P with T. Okay, a question for us to try. We know that for an adiabatic process, PV to the gamma is equal to some constant. Evaluate this constant for an adiabatic process involving exactly 2 moles of an ideal gas passing through the state having exactly P is 1 atmosphere and T is 300 Kelvin. Assume a diatomic gas whose molecules rotate but do not oscillate. Okay, so we've got PV to the gamma is equal to a constant, and we have to find out what this is. We're told the number of moles is equal to 2.00. The pressure is 1 atmosphere, which we can write as 1.01 times 10 to the 5 pascals. And the temperature is 300 kelvins. We're told it's diatomic and it rotates but does not oscillate, which tells us that F is equal to 5. 3 translational degrees of freedom plus 2 rotational. Now the easiest way to solve this problem is just to work out what P is, what V is, and what gamma is. We've already got P here. To work out V, we should use the ideal gas law. PV is equal to nRT, which tells us that V is equal to nRT over P. So N is 2, R is 8.314, T is 300, and the pressure is 1.01 times 10 to the 5. Solving that on the calculator, we end up with 0.04939 meters cubed. Now we've got V as well, so we just need to calculate gamma. Gamma is equal to Cp on Cv. Cp is equal to Cv plus R over Cv. Now Cv is F over 2R plus R over F over 2R. Our R's will cancel out and we end up with F plus 2 over F. And we've seen that F is 5, so this is 7 over 5, which is 1.4. Okay, now all we need to do to find R, a constant, is substitute in. P is 1.01 times 10 to the 5 pascals. V is 0.4939, whoops, we left off the 0, meters cubed, and then gamma is to the 1.4. So we solve that on the calculator, and we end up with 1,498, which is equal to 1,500. Now, strictly speaking, we should always give units. The units in this case are very strange units. We've got P, the pressure is measured in pascals, and then this is the volume to the power of 1.4. So this is meters cubed to the 1.4. So the units are PA. 3 times 1.4 gives us 4.2. So it's meters to the power of 4.2. So those would be our very strange units. Now we're going to run through a number of definitions. It's very important that you are familiar with these definitions. Most of them are fairly obvious from the names. So an isothermal process is one that's carried out at constant temperature. So for an isothermal process, there is no change in internal energy. And we also know from the ideal gas law that PV is constant. So if you see that something's isothermal, you can immediately assume these two equations. An isobaric process is a process carried out at constant pressure. Heat and work are generally not zero. In this case, the ideal gas law tells us that T on V is constant, and we saw in the last lecture that the heat transferred into the system is given by N Cp delta T. An isovolumetric process is one that takes place at constant volume. When the volume does not change, no work's done. So work is equal to zero, and so the change in internal energy from the first law of thermodynamics is just equal to the heat flow. And we saw last lecture that the heat flow is equal to NCV delta T. Now here's something for you to try. Name each of the paths A, B, C and D on the PV diagram below. One of them is adiabatic, one is isovolumetric, one is isobaric and one is isothermal. Along path A, the volume is kept constant, so this is the isovolumetric process. Along B, this has got the shape of an adiabatic curve, so B is the adiabatic process. C takes place along an isotherm, so this is an isothermal process. And for process D, the pressure is kept constant, so this is the isobaric process. Okay, a question. A monotonic ideal gas initially at 300 kelvins undergoes an isobaric expansion at 2.50 kilopascals. If the volume increases from 1 meter cubed to 3 meters cubed and 12.5 kilojoules is transferred to the gas by heat, what are A, the change in internal energy, and B, its final temperature? To answer this question, we should start by drawing a PV plot. We're told that it's an expansion from 1 meters cubed to 3 meters cubed at a constant pressure of 2.5 kilopascals. We're told that while it's undergoing this expansion, heat is transferred in and the amount of heat is 12.5 kilojoules. A good technique to use when answering these questions is to write what you know of Q, W and the change in internal energy above the path on the PV plot. Okay, now part A asks us to calculate the change in internal energy for this case. We've got Q, we can easily calculate W, as W is just the area under the PV graph. So in this case, it's 3 minus 1, which is 2 times 2.5, which gives us 5.0 kilojoules. The kilo comes about because we've got kilopascals over here. Now this is an expansion, so the work done on the gas is negative. Change in internal energy, according to the first law, is just the sum of these. So it's 12.5 minus 5.0. This will be in kilojoules. And that is equal to 7.50 to 3 significant figures kilojoules. Okay, part B asks us to calculate the final temperature. And we're told that the initial temperature here is equal to 300 kelvins. Now we know that this is an ideal gas, so the easiest way to solve it is that the initial temperature over the initial volume is equal to the final temperature over the final volume, because we've got PV is equal to nRT. Rearranging this, we've got T over V is equal to P over nR, and this remains constant in this case, so T on V remains constant. Okay, so substituting in, we've got 300 over 1 is equal to TF over the final volume, which is 3. So that tells us TF is equal to 3 times 300, which gives us 900 kelvins. Okay, the next part. The figure on the slide after this question shows a cycle undergone by 1 mole of an ideal monotonic gas. The temperatures are T1 is 300, T2 is 600, and T3 is 455 Kelvin. From 1 to 2, what is the heat, change in internal energy, and work done? Same questions for from 2 to 3 and 3 to 1. And then for the full cycle, what are the heat, internal energy change, and work done? And then the initial pressure at point 1 is 1 atmosphere. What are the volume, the pressure at point 2, and the volume and pressure at point 3? Okay, and this is our diagram here. Okay, to start with, let's write down everything we know. We know that N is equal to 1.00, and we know that it's a monotonic ideal gas, so F is 3. The temperature at point 1 is 300 kelvins, at point 2 is 600 kelvins, and at point state 3 is 455 kelvins. To start with, we're asked to calculate the heat flow, the work done, and the change in internal energy going from 1 to 2. Well, going from 1 to 2, the volume's not changing, so that immediately tells us that the work is equal to 0. Now, we can either calculate the heat using the CV case, or we can calculate the change in internal energy. Let's do the change in internal energy. The change in internal energy is equal to F on 2 nR delta T. So in this case, we've got 3 over 2 times 1 times 8.314. Now the final temperature is 600. The initial temperature is 300. So that's the change in temperature there. So the change in internal energy is 3,741 joules. Let's just write it on our diagram. Now our first law tells us that the change in internal energy is the same as the heat flow plus the work done. So Q is equal to 3,741 joules as well. Okay, next we're asked about path 2 to 3, and we're told this is adiabatic. So adiabatic tells us straight away that Q is equal to 0. Okay, now it would be hard to work out the work because we need to work out the area under this curve. We could do it because we do have an equation for this line, PV to the gamma, and we could use 3 to work out what gamma was. But that's hard. It's much easier to work out the change in internal energy. So the change in internal energy, we just need to substitute into this equation again. We've got the change in internal energy is equal to 3 over 2 times 1 times 8.314 times the final temperature, 455, minus the initial temperature. Solving that on your calculator, you should end up with minus 1,808 joules. So the change in internal energy is minus 1,808 joules. And so that tells us that the work done will be the same as the change in internal energy, minus 1,808 joules. Okay, we expect it to be negative as this is an expansion. Okay, now we need to do it going from 3 to 1. Okay, to work out the change in internal energy, we can once again substitute into this equation. 3 over 2 times 1 times 8.314 times the final temperature, 300 minus 455. Solving that on the calculator, we end up with minus 1,933 joules. So this is equal to minus 1,933 joules. Now it's actually not easy to work out the work for this case because we don't know what this pressure is. We haven't been told the scale on this axis. So what we can do is work out the heat. This is the constant pressure case. So Q is equal to NCP delta T. And this is 1.0 Cp is equal to R plus Cv, which is R plus F over 2R times the change in temperature. So the change in temperature is the final temperature minus the initial temperature. Okay, so F is 3, R is 8.314. Solving that on the calculator, we end up with Q is equal to minus 3,222. And now we can work out the work just using the first law of thermodynamics. We know that the change in internal energy is equal to the work done plus the heat added. In this case, the heat's removed. And so that gives us work is equal to 1,286 joules. Okay, so that's the first 9 parts. We were then asked to do it for the cycle, so going from 1 to 2 to 3 and back to 1. Now, since we end up at the same state, at the same temperature, we know that for the cycle, the change in internal energy is equal to 0. Let's just check that. We can add each of these internal energies together. We end up with 3,741 minus 1,808 minus 1,933. When we do that, do indeed end up with 0. So this would have actually been an alternative way to calculate this last change in internal energy. Okay, for the cycle Q, the heat flow, we just have to add up each of our heat flows. So 3,741, this one's 0, minus 3,222. This gives us 519 joules. And now the work done, we'd expect these two to cancel out because of the first law of thermodynamics to give us 0. But let's just check. We can add up the work done along each path. Minus 1,808, there's none here. And here there's 1,286, which gives us minus 522. Very close. We'd expect these to be the same. They're just going to be slightly off because of dropping decimal places and things along the way. So they should really be the same. Okay, so that's for the cycle. Okay, we were then told that we can assume that the pressure at point 1 is 1.00 atmospheres, and we were asked to calculate the pressure and volume at point 2. So this is a constant volume case, so the volume is not actually going to change. So if we calculate the volume at 1, that will tell us the volume at 2. So just using the ideal gas law, PV is equal to nRT, we have V is equal to nRT on P, 1, 1. So this is 1 times 8.314 times the temperature at 1, which was 300, over the pressure at 1, 1.01 times 10 to the 5. Solving that on the calculator, we end up with 0.0247 meters cubed, and the volume's not changing, so this is also the volume at 2. Okay, now we need to calculate the pressure at 2. So we can just use the ideal gas law. The pressure at 2 will be equal to nR times the temperature at 2 over the volume at 2. Substituting in, that's 1 times 8.314 times 600, all over the volume at 2, which is we've calculated over here as 0.0247. Solving that on the calculator, we get 2.02 times 10 to the 5 pascals, which is equal to 2 atmospheres. So because we've doubled the temperature, we've actually doubled the pressure as well. Everything else was kept constant. And then we're asked to calculate the pressure and the volume for point 3. Well, it's got the same pressure, so the pressure is equal to 1 atmosphere. And then we can just use the ideal gas law to get the volume. Volume is equal to nRT over the pressure, which is equal to 1 times 8.314 times 455 over 1.01 times 10 to the 5. Solving that on the calculator, we end up with 0.0375 meters cubed. So that's the volume at point 3. So that looks a bit of a mess, but we've solved it all now. Obviously, in an exam, you'd be wanting to label them as the answers to A, B, C, and D. But it's always a good idea to write what you know on the diagram. Okay, a gas can be expanded from initial state I to final state F along either path 1 or path 2 on a PV diagram. Path 1 consists of 3 steps: an isothermal expansion, work 40 joules in magnitude, an adiabatic expansion with 20 joules of work done in magnitude, and another isothermal expansion, work 30 joules in magnitude. Okay, these are all expansions, so the work's going to be negative in each case. Path 2 consists of 2 steps: a pressure reduction at constant volume and expansion at constant pressure. What is the change in internal energy of the gas along path 2? Okay, now it doesn't matter if we use path 1 or path 2, as they have the same initial and final states, and so the change in internal energy will be the same between them. To answer this question, let's draw a nice big PV diagram. Here's P, here's V, here's initial state I, and here's our final state F. Path 1 consists of an isothermal expansion, an adiabatic expansion, and then another isothermal expansion. Okay, probably not the best drawing. This one's isothermal, so isothermal tells us that the change in internal energy is equal to 0. We're told in the question that the work done is 40 joules in magnitude. It's expansion, so that's minus 40 joules. Along the second part, we're told that this is adiabatic, which means Q is equal to 0, and we're told that the work done, again it's going to be negative, is 20 joules, so minus 20 joules. This third part is again isothermal, so no change in internal energy, and the work done, we're told, is 30 joules, and that will be negative as it's an expansion. Path 2 consists of a pressure reduction at constant volume and then a volume increase at constant pressure. So this is path 2, and here's our path 1. And we're asked to find the change in internal energy. Well, since the change in internal energy doesn't matter if we use path 1 or path 2, let's use path 1. We've got the internal energy for this step and for this final step here. We can get it easily for this step using our first law of thermodynamics. The change in internal energy is just the Q plus the W, which is equal to minus 20 joules in this case. So the total change in internal energy is 0 plus minus 20 joules plus 0. So that just gives us minus 20 joules as our final answer to that question. An ideal diatomic gas with rotational but no vibrations undergoes an adiabatic compression. Its initial pressure and volume are 1.2 atmospheres and 0.2 meters cubed. Its final pressure is 2.4 atmospheres. How much work is done by the gas? Okay, the best way to start this question is once again to sketch our PV plot. Now we're told that it's an adiabatic compression, so it's going to go from some initial state to some final state with a smaller volume along an adiabatic type curve. So up like that. Okay, we're told its initial pressure is 1.2 atmospheres and its initial volume is 0.200 meters cubed. Its final pressure is 2.4 atmospheres, and we're not told its final volume. We are told that it's adiabatic, which means that Q is equal to 0. We're also told that it's diatomic and that the particles are rotating but not vibrating, which tells us F is equal to 5. The 3 translational degrees of freedom plus the 2 rotational ones. And as it's adiabatic, we know that it obeys the equation PV to the gamma is equal to constant. And what we're asked to find is the work. We're actually asked to find the work by the gas. Usually we're asked to find the work on the gas. So what we need to do is find this area somehow. Unfortunately, this question is actually quite hard. So to start with, we need to calculate what gamma is. Gamma is equal to Cp on Cv, which is F plus 2 onto R over F onto R. Cancelling out all the common factors, we've got F plus 2 on F, which in this case is 5 plus 2, 7 over 5, which is 1.4. So we can use this now to find the final volume, as we've got the initial and pressure and volume and the final pressure. So we've got P initial, V initial to the 1.4 is equal to P final, V final to the 1.4. We can keep our pressures in atmospheres as long as we do it for both of them. So this is 1.2 times 0.200 to the 1.4 is equal to 2.4 times V final to the 1.4. Okay, we can solve this. Divide 2.4 by 1.2 and we end up with 2. And then we can write 1.4 log 0.200 is equal to log 2 plus log 1.4 log VF. These are just numbers. You can work out what they are on your calculator and then divide by 1.4 and we end up with log VF is equal to minus 2.10, and so VF is equal to e to the minus 2.10, which is equal to 0.122 meters cubed. Let's just check it's reasonable. This is a compression, so it should be smaller than this one. So 0.122 meters cubed looks very reasonable on that plot there. Now, to work out the work, we need to work out this area. Okay, now unfortunately we really do have to do this integral. So the work is equal to minus the integral from the initial velocity from the initial volume to the final volume of P dot dV. We need to substitute in for this P, so we can rearrange this to give us P is equal to the constant times V to the minus gamma. dV, we've still got our dV, so that's our P. Okay, now we want to integrate this. The constant's just a constant, so it can go out the front. When we integrate this, we end up with V to the minus gamma plus 1 over minus gamma plus 1. Oh, we dropped our negative sign there, so we need to put that back. And that's at VF and VI. Okay, now to evaluate this, we need to work out what this constant is. So this constant's up here. We can use the initial state. So the constant is equal to Pi Vi to the 1.4. Pi is 1.2 times 1.01 times 10 to the 5. Vi is 0.200, and that's to the power of 1.4. Solving that on the calculator, we end up with 12,733. If you want to include units, then it'll be pascals and meters cubed to the 1.4, so meters to the 4.2. Okay, so now let's substitute everything in here. We've got, let's get rid of that negative sign, so we can make that positive. This is positive and that's negative then. So we've got 12,733 times, this is V final, which is 0.122 to the 1 minus 1.4, so that's to the minus 0.4 over 1.4 minus 1, so over 0.4. And then with we substitute in the initial volume, so that's 0.200 to the minus 0.4 over 0.4. Solving that on the calculator, we end up with 13,249, so that's equal to 13.2 kilojoules. That's the work done on gas, which means that the work done by the gas is minus 13.2 kilojoules done by gas. Okay, and that's the answer to this question, and that's the end of the lecture.